Hello and welcome to an episode that deals with geomorphic indices. I am Dr. Vimal Singh from Department of Geology, University of Delhi. Today we will discuss about the geomorphic indices and its application. We will discuss about some of the most commonly used geomorphic indices and how to calculate them and what does their result mean. After studying this module, you shall be able to know about the geomorphic indices and their uses, learn about the most commonly used geomorphic indices in tectonic geomorphology, learn the methodology of calculating various geomorphic indices, know about what does results of various geomorphic indices mean. Now we look at the geomorphic indices. The basic characters of landforms that can be measured are, we can measure their shape, sizes, areas, elevation, slopes and slope directions. And these measurements, it allows us to calculate parameters which we call it as geomorphic indices, thereby enabling comparative analysis between different areas and regions. So, if we have two regions, we can measure these parameters and we can compare the two areas. Some of the geomorphic indices that we are going to look at today have been developed as basic investigation tools to identify areas undergoing rapid tectonic deformation, whereas others were developed as quantitative descriptors of landforms. Following geomorphic indices that we are going to discuss are commonly used in active tectonic studies. Which are these? The first one, which is the most common one, is the mountain front sinuosity ratio. The second one is basin asymmetry. Third one is ratio of valley flow width to valley height, and the fourth one is Hack profile and stream length gradient index, and the fifth one is hypsometry. Now, these geomorphic indices allow us to comment upon or to assess any given area for tectonic deformation. Now, the commonly used geomorphic indices that we are going to discuss today is, the first one is the mountain front sinuosity ratio. Before talking about this ratio, we must know that what is mountain front. Now, a mountain front is defined as a major fault bounded topographic escarpment that marks the boundary between mountainous topography and relatively flat topography with relief exceeding 20 meters. Now, mind it, it is very important to note here that the topography that we are seeing where the relief is more than 20 meters, it should be an escarpment and it should be bounded by a fault, right. So, that will be called as a mountain front. Now, the mountain front sinuosity ratio, it is used to classify the long term tectonic activity. An active front is generally straight, whereas inactive one becomes increasingly embayed. Now, this ratio was developed by Bull and McFadden in 1977. They used this method to evaluate relative tectonic activity north and south of the Garlock Fault in California. Since then, this ratio has been used by several other workers in different terrains of the world. Now, the principle behind this geomorphic index is that if a fault is active and experiences regular uplift along it, then the river will have to continuously incise vertically. As a result, the deviation of the line defining junction between the mountain and the adjoining Piedmont is nearly straight. So, if you have a fault which is active and the topography is uplifting, any river that is flowing through that or across that, what it will do? It will try to compete with the uplifting terrain and it will keep incising. So, as a result the valley will be narrow and the mountain Piedmont junction boundary, it will be nearly straight. On the other hand, if a fault is inactive, then the river crossing the fault after attaining a steady state will widen laterally. Okay. So, in this case what will happen? The ratio that we are seeing between the mountain and Piedmont, it will be much more. Okay. So, it will result in a boundary line that greatly deviates from the straight line. So, if the line is straight, you get very low value, and if the line is deviating a lot, then you will get a high value. This helps us to comment upon the nature of the fault. Now, the sinuosity is calculated by dividing the length of the mountain Piedmont junction, which is called as L, by the length of the associated range, right. So, now if we take any topography, we may have a straight line that will be the length of the range, and then the mountain Piedmont junction, it will be LR. Okay. And when we divide the two, what we get is the mountain front sinuosity ratio. Okay. So, in general the mountain front sinuosity can be measured from any topographic map or a contour map, and usually what we do is we take the contour defining the mountain and the Piedmont boundary, and we measure the length of that Piedmont. One thing that should be noticed and kept in mind while calculating this ratio is that a terrain can be having different climate, it can be having the rocks that are composing the topography, it can be of different nature, it could be a soft rock in some areas, it could be of very hard rock. So, these ratios that we are calculating are not really sensu stricto similar for all the terrains. So, that should be kept in mind while calculating this ratio. So, in general the mountain front sinuosity can be measured using topographic map or a digital elevation model. The length of L could either be measured directly by measuring the contour defining the junction between the mountain and the Piedmont, or it can be measured by drawing a line along the mountain and Piedmont junction. The length of the L is the length of the straight line marking the boundary of the mountain. It should be noted that it is not necessarily that this line should be straight, because some of the faults are curved, and especially in thrusts or the reverse faults. The next geomorphic indices that we are going to discuss today is basin asymmetry. Now, this is another method that helps in recognize tectonic deformation in an area. In the regions of active tectonic deformation, the drainage network often has a distinct pattern and geometry. Now, the asymmetry method was developed to detect tectonic tilting at drainage basin scales or at regional scales. The asymmetry factor can be calculated by comparing the area of the total basin with the area of the basin on the right hand side of the main stream. Now, this is given by the formula A equals to 100 multiplied by AR, that is the area of the basin to the right of the main stream, to the divided by the total area of the basin. Now, if A is 50, when a stream, then the stream network is flowing in a stable area and the basin is perfectly symmetric. Now, the area is sensitive to tilting along the perpendicular axis of the basin. Now, if there is any tilt, that will result in the change in the area. Now, the values of A greater or less than 50 may suggest tilt. Now, this method it should be noted that it works best where each drainage basin is underlain by similar lithology, and this method also assumes that neither lithological control such as dipping sedimentary layers nor localized climate such as vegetation, differences between north and south facing slopes cause the asymmetry. Now, if you have a basin, now that basin may get tilted due to any tectonic activity. If the tilt is towards the right, then it will have more area on the left and the value of the asymmetry factor will be less than 50. And if the tilt is towards the left, then the area on the right side will be more and the value will be more than 50. The methodology of calculating the drainage basin asymmetry is that we can calculate this either from the topographic map or from a digital elevation model. Now, drainage basin and the longest drainage are required to calculate asymmetry in a basin. The total area of the basin and the area to the right side of the trunk river need to be calculated. Ratio of the two values will give us the basin asymmetry. Now, the third important geomorphic index that we are going to discuss today is the ratio of valley flow width to valley height. Now, this index reflects the adjustment of the stream between downcutting and lateral erosion. Deep V-shaped valleys will form in areas of high uplift and yield low V values. Broad flowed canyons will be associated with low uplift rate or tectonically inactive areas, and it will yield high V values. V value is the ratio that we are talking about. This can be calculated by measuring the valley measuring the width of the valley floor, elevation of the left valley divide, elevation of the right valley divide, elevation of the valley floor. If we have these parameters, we can calculate the valley flow width to valley height ratio. When calculating V, these parameters are measured at a set distance from the mountain front. It is not that we can measure it everywhere, but it should be measured at a set distance. Now, high values of V are associated with low uplift rates, so that the streams cut broad valley flows, because if the tectonic activity is low, then the floor of the valley will be widening, whereas if the uplift is more, then the low values of V will come. Okay. So, it means that low values of V reflect deep valleys with streams that are actively incising, commonly associated with the uplift. Now, the parameters required for the analysis can be taken from again from the topographic maps or from the digital elevation model. The Hack profile and stream length gradient index. Now, this is an important geomorphic index and it is widely used. A method of analysis of the longitudinal stream profiles was developed by Hack in 1973. Simple semi-logarithmic graph of the stream profile forms the basis of this analysis. An ideal graded river on uniform substrate plots as a straight line when plotted on a semi-logarithmic graph. The slope of a straight segment on semi-logarithmic plot is k, which is equal to the product stream length, or it is called as the stream length gradient index. The gradient of smaller reaches of the stream except near the source can be calculated using the formula SL equals to delta H by delta L multiplied by the length, where delta H and delta L is the slope of the reach and L is the length of the stream from the source to the midpoint of the reach that for which we are measuring this ratio. Okay. So, if we have a small reach, so it can be measured for smaller reaches and it will give us certain value which is the stream length gradient index, and these values will tell us that whether there is any anomaly or not. The parameters that are required to calculate SL index value can be collected from topographic maps or digital elevation model. The SL index value for segments between two successive contours can be calculated for our ease. Now, for the hack profile analysis, the distance between the contours can be measured and this distance can be plotted against the elevation at different points. Now, in this remember that not only the high values, but at times the low values can also suggest us that an anomaly is present along a longitudinal profile. This analysis has been successfully used to identify active faults in different terrains and especially in the Himalaya. The next important geomorphic index that we are going to talk about is hypsometry. Hypsometric curves are a non-dimensional measure of the proportion of the land surface above a given elevation. This was developed by Strahler in 1952. So, Strahler recognized that the significance of the shape of hypsometric curve, and he identified three types of landforms and he called it as young, mature and monadnock. The hypsometric integral is the simplest way to characterize the shape of the hypsometric curve of a given drainage basin. Area under the hypsometric curve is called as hypsometric integral and it can be calculated by a formula which is H equals to mean elevation minus minimum elevation divided by maximum elevation minus minimum elevation. The hypsometric curves are very useful because they are independent of different basin sizes and relief. So, we can have a very large basin, we can have a very small basin, yet we can compare their hypsometric integral. It is a powerful tool in the field of neotectonics as it helps in differentiating tectonically active regions from the inactive ones. For a selected basin, the range of elevations is divided into equal intervals. For basins that are under investigation, the interval can be calculated or it can be taken by whatever we want to carry out. Now, for each interval, the proportion of the basin area is calculated. Now, the elevations are normalized by the relief of the catchment, so that it ranges from 0 to 1. Now, when we get the values of hypsometric integral, then the values which are close to 1, they suggest that tectonic uplift is more than the erosion in the basin. But if the erosion dominates, then the value will be less than 0.5 or 0.4. And if it is in the range of 0.4 to 0.5, we often say that the rate of uplift and rate of erosion is quite similar. Another index that we are going to talk about is tilting of alluvial fans. Now, this index is not very commonly used because of problems in carrying out this analysis, but it is very useful. Under geometrically simple and tectonically stable conditions, most of the alluvial fans are conical in shape, and the topographic contours across these cone shaped fans approximate segments of evenly spaced concentric circles. Now, it was recognized in 1970 that if a conical fan is tilted, contours across this fan become segments of ellipses. In 1991, West worked out in detail the changes in the shape of conical fan subjected to tilt. Change of contours from circles into ellipses is it is sensitive only to horizontal component of rotation, whereas in the opposite case rotation about vertical axis will pivot a fan without altering the shape of the contours. You can find the solution for a tilted cone in the e-text that is available. So, when we calculate the tilt in an alluvial fan, it not only tells us about the tectonic deformation in the fan, but there is a methodology from which we can also calculate that how much uplift is required to tilt the fan for that many degrees that we have calculated. Though it is very useful technique, but it is used very less because of the problems in fitting the ellipses on the contours of the alluvial fan. Okay. So, today we learnt about what is geomorphic indices and also about some of the most commonly used indices for identification of tectonic activity in a terrain. That is all we have for you today. We hope you enjoyed the session. See you again. Till then, thank you and namaskar.